Yeah. Yeah, probably
So Liz, I'm not tethered to these microphones, right? I can Sorry? Oh, should I use that?
Yeah.
Okay.
Put that on your tie. And then put that in a pocket.
Okay.
There you go.
I understand. Okay.
And then there's a little on button right there. That you can turn.
Press it. Right. Okay, got it.
We don't have the Hello? Is it on?
I think you can just speak.
Yeah.
Testing.
Okay, so if you have that, then you're good.
They were asking.
What?
Catherine.
I think those aren't on yet, but
Hello? It's fine. I did flip You can just go, Catherine. Oh. Overhead mics, too. If you...
green on the top.
It's green, yeah.
Okay, welcome back from lunch. Today, I'm very excited to chair session 3, which will focus on 3D reconstruction of stars in the ISM / unveiling the ISM through the absorption and scattering of starlight. And I'm very, very excited to welcome our invited speaker, Bob Benjamin, who will be talking about energy inputs in the local interstellar medium.
Okay, well, thank you very much, Catherine. So I'm starting off with a picture I'll get to it near the end of the talk, but I just wanted to start off with, this is sort of a paper by Lewis McCallum, just published a few months ago. It's a comparison of the observed H-alpha, which is what has all the labeling, centered in the galactic anti-center, with a model of the H-alpha sky that did not involve anything about H-alpha. Okay, and so I will get to this in a second, but I just wanted to start off so you stay awake until we get to this point. So I'm going to talk a little bit about some history because those of you who know me, I'm a history guy, and then the birth of stellar clusters in the solar neighborhood, the kinetic energy density in the solar neighborhood, and then ionizing the solar neighborhood. So this is all basically, as you've heard about earlier, in this sort of area, this little patch of the galaxy, which has basically been turned into a high-resolution interstellar and stellar physics laboratory. So let's go ahead and start off with a story. So I don't know how many of you know this story, so I felt like I had to tell it. It's the story of the beginning of the study of the interstellar medium by Lyman Spitzer. He wrote a paper in the 1938, well, he had a draft in the 30s, came out in 1941 eventually. He says, this paper had its genesis in 1938-39 when I was a postdoctoral fellow at the Harvard College Observatory. I remember well the excitement occasioned by Beta's pioneering work that year, showing that the energy radiated by the brighter stars was generated by nuclear fusion via the CNO cycle, converting hydrogen to helium. Martin Schwarzschild and I had lively discussions of this result, whose consequence seemed to be that supergiant stars could not have been shining at their present rate since the formation of our galaxy. We concluded that that these extremely luminous stars must have formed relatively recently. The dust clouds and spiral galaxies provided a likely site for the birth of these stars. Based on that initial moment of excitement, he actually constructed an entire theory of how you could take interstellar matter and convert it into stellar systems, outlining the properties of stellar systems, globular and disk-like, and then trying to develop a deductive theory of the entire interstellar medium. He gave it to his colleagues. His colleagues said, you know, tone down the metaphysical introduction, and then he finally revised it, which it came out in 1941. But in the process of trying to build a model starting with the interstellar medium and ending up with the properties of stellar systems, he realized, as attracted as I was by broad inclusive theories, I assembled the arguments given this paper and even inspired to develop this point of view as an entirely deductive theory with the results of table 1. This is table 1. All following inexorably from the difference of angular momentum between flattened spirals and globular star systems. By the time I moved to Yale the following year, I realized that our basic information on the properties of the interstellar medium was grossly inadequate for any portion of this grandiose theoretical project. So I embarked on a long-range program to analyze various physical processes in interstellar space, a project in which I have been engaged off and on for much of my career. So that was sort of the beginning of the stellar-interstellar connection. And I tell this story in particular because actually at the beginning part of my career, I only had the opportunity to meet Lyman Spitzer once in person, and it was in this room right over there. And so it's really a thrill to come back here and talk about the interstellar connection. So, first chapter, I'm going to talk a little bit about work done by 3 collaborators, and my level of involvement has been medium, I would say, in Cameron's, lower in the next one I'll describe, and then very high in the final one. This is a paper, if you do not know about it, I encourage you to learn about it. The title says it all, most nearby young star clusters formed in 3 massive complexes. So I'll describe what the research was as we watch a little animation. Thanks to Gaia, we can identify clusters and cluster members. We can measure the positions of these stellar clusters very well and get the 3D velocities of them. Proper motions coming from Gaia and then other things supplementing the radial velocities. And around the sun, Cameron identified a set of clusters that when he evolved them backwards in a reasonable galactic potential, did something interesting. Now, this is not all the clusters, but it's about 2/3 of them. And about 30 million years ago, you'll notice that these clusters scattered in the current day all around the sun turn into 3 separate groups. So these clusters seem to basically not just be individual objects, they are families. They come in families of clusters. And I think Catherine might have been the one that suggested calling them families, which was a brilliant stroke of genius there. And so those families formed starting around 45 million years ago. An interesting implication of this is that the clusters, we can actually date the clusters and get their ages. And so we're tracing them back in many cases to times before they were formed, which would mean that we were tracing the parent molecular cloud's trajectory. But it does seem to work that they all trace back to 3 spots in the solar neighborhood. And so here, meet the families. They were named by Cameron after 3 prominent clusters within the family, so Colander 135, M6, and Alpha Per family. There's 39 clusters in this one, 34 in this, 82 here. That's a little bit misleading because they combine both clusters, but also what are called young local associations, which don't quite make the cut to be clusters. But the ages of these things, based on the fitting color magnitude diagrams, is sort of 20 to 30 years on the average. The number of supernovae you expect from the clusters ranges from 63 for this one, 124, 61. A total of about 200 supernovae would be associated with the clusters, and original stellar masses in total of about 10 to the 5 solar masses. You can infer an initial parent cloud gas mass of about 1 million solar masses. The clusters are typically spread out over a 200 parsec area currently, but at their most compact, trace back to more like 50 to 100 parsecs. And they were at their most compact configuration 20 to 30 million years ago. So why is this important? Oh, and then of course, this just shows their sky distribution. The purple ones are the Alpha Per family, and they're spread out all over the sky because they're the closest ones to us. They're spread out all over the place. Colander 135 family is over in one direction, and M6 spread out a little bit more. And then these are some little thumbnails of some of the individual clusters. I should mention there is also a fourth very small family that Andy mentioned. It's this one, or the Colander 135 family, that might be responsible for the Gum Nebula and that bulb and the IRAS shell. If you take these clusters and you estimate the amount of supernovae, there's a lot of energy that will be pumped into the ISM over this 40 million year time interval, okay? And so Cameron pointed out that this could explain some of the larger interstellar structures that we've been hearing about in the previous session. So we have the local bubble. Catherine already identified some clusters that could be responsible for this, but Cameron confirmed that result. There's this giant supershell here. There's a band of emission just outside the sun's orbit. By the way, just everyone, this is the same orientation as everyone else. So galactic center is to the right, L of 90 this way. And this is sort of a plus or minus 1 kiloparsec box around the local bubble. And so you can look at the cluster positions now, and you see the M6 currently is here, sort of partially in that giant supershell that was first identified by Carl Hylas in the late 80s, I think. And then the next family of clusters is the SCO-SEN family. Again, the reason this is so good in terms of being local is because it does include the young local associations, which were added to the families. But you can see it looks like it has a lot to do with the structure of things right around the sun, and possibly some of the structure up here. And then finally, there's the Colander 135 family. This one, I think, had the best case in Cameron's paper for trying to match up what we see in the interstellar medium, which is this. So Cameron took the properties of that expanding H1 supershell, along with models of supershell expansion, and you can infer an age of about 30 million years for this supershell, and a total number of supernovae that are about 90 or 100 supernovae to create this giant supershell. This assumes expansion velocities, mean ambient density, radius, and so on. And that is to be compared with what we know about the families of these clusters. The age of the Colander family is about 22 megayears, not a bad match to this age. And the number of supernovae is 63, which is not as close to 96 as you would hope, but it turns out that some of the M6 clusters have also wandered into this region. Okay, and so you can make a consistent case that the combination of mostly these clusters, but then additional clusters that carved out this giant supershell that abuts the local bubble in this direction. So I never really dreamed this was possible, and so it's been a thrill to be involved with it. Another thing I would just want to point out is that this is not one burst of star formation, not a one and done kind of thing. There's been a series of extended star formations starting about 45 million years ago, ramping up to about 20 to 30 million years ago, and then at least in these two families ramping down. Here, this is, again, not a fair comparison because it includes the youngest, smaller associations. You get a slightly different time profile. And this is not showing you the total number of stars formed in the cluster, but just the numbers of clusters of a given age in the three different families. But the main point has been there has been a history of star formation. So it's not just that we know the number, we actually can put a time profile in for how much energy might have been injected into the solar neighborhood. So that leads to the next paper. What is the effect of these supernovae on the local interstellar medium? This is a paper by Juan Soler. Other people are also working on this, trying to estimate, because we have these maps of the 3D density of dust, we have the mass of the dust, we have the position of the dust. What we would love is the 3D velocity. What we'll have to accept is the radial velocity, unless we have ways of getting the 3D velocities of gas clouds, possibly by association with YSO groups. And so what Juan did is he actually took the 3D dust maps now available and tried to link up in the same way that Theo described in the morning, basically clouds seen in velocity space with clouds seen in dust 3D space. This is a lot harder than it sounds, and so there's, I think, going to be a period of shakeout in this technique. But the method that Juan uses is something called the HOG, the histogram of oriented gradients. I am not going to describe this because I probably would describe it poorly. But the basic idea is you can identify two structures in two different maps by looking at the gradient, the drop in the intensity as a function of direction. And if they have aligned gradients, they may be associated objects. So this shows just, again, In order to do this, though, you have to take a chunk of the sky and say, I want to match this chunk of the sky in dust and this chunk of the sky in gas. So this requires sort of degrading the resolution and with constant angular spins, okay? So the 3D dust maps have been sort of sectorized here, and you can see how the sectorization sort of washes out some of the information in physical space, but allows you to therefore to match it to velocity space. And so this is the density. This is basically a statistical measure of how well you have a good match between H1 or the H1 maps of the sky, or then the dust maps of the sky in a given direction at a given distance. So in other words, when this number is high, you have a very good match at a given cloud of a given distance to a particular cloud at a given velocity. And so with that, and then this is the same thing with the CO. So this is just to show you an example of what this means. What this means is this sort of statistics of measure, the Rayleigh projected Rayleigh statistic, is high here. That indicates that the gradients are aligned. So there's a high probability that a dust cloud seen in one channel matches a velocity cloud seen in different, in velocity space. And so here's the sort of a way of quantifying that. So there's distance for the dust maps on this axis, velocity on this map axis for the CO maps, and you find a sort of highest measure of the statistics at this combination of distance and velocity. And so what does that look like on the sky? Here's the CO map on the left, and here's the H1 map and the dust map. The H1 is at the same velocity. The dust map is in what we think would be the corresponding distance channel. And so you can see it's doing its job in assigning a velocity to a given distance or distance velocity. Using the sectorized version of the local galaxy, this is what the rotation of the galaxy would look like if you just had nice uniform circular rotation using the Mark Reed rotation curve. This is where you get this is what you would get for the H1, the velocities of the well-matched H1 clouds. So it looks sort of like rotation. In other words, it's blue, red, blue, red, blue. But there's deviations from that, which means there's deviations from circular rotation. And this shows the CO as well. So the bottom line here is you can then look at the difference between the line of sight velocity as matched to at a given place in the galaxy to the expected rotational velocity at the same point of the galaxy, make a histogram of it. Take that and look at the difference between those two, subtract off the rotational motion, and make an estimate of the total kinetic energy density at a given location in the galaxy. I want to say that I think this is sort of in its early stages. There will probably be better ways of doing this and more complete. But this is a really, I think, impressive first effort in this area. It's not really the first effort because Josh and Kirill, is it Chernyshov, really pioneered this, but in a day where we didn't have the Gaia distances in the way we have now. So anyway, so the bottom line here is that we have a turbulent energy density. And it's not once you account for the fact that this is only one of the three components, right? Because you're only measuring line of sight. It's not inconsistent with what people have claimed for the energy density of the quote unquote random motions in the solar neighborhood in the past. But what's different is you can map it. You can say, here's an area where there's excess kinetic energy. Here's an area, so you can actually start to map the injection of energy into the local interstellar medium as measured by deviations from the rotational flow. So I think that's another advance. And now for the final part, I'm going to talk about something that really, it has no basis, no reason to work as well as it did, but I think that is telling us something. This is a paper by Lewis McCallum called The H-alpha Sky in 3 Dimensions. And now we're back to this picture. So again, this is a simulation of the sky. And then this is the actual sky as measured by the Wisconsin H-alpha mapper. How did we make and some of the famous objects here, remember this is only within 1.25 kiloparsecs. So there are certain regions like here, the Carina region, and then the Sagittarius region right over here. You'll see them in the data, but they disappear in the model because they lie outside the scope of our model. Okay, so that's why those things are not there. There are also some H2 regions off the plane that you will not see in our simulation because those are produced by B stars. And the simulation that we did here was involving only O stars. So there's still some work to be done on this thing. But here's how it worked. We took the dust maps, and this may look familiar, but it's familiar with a twist. What Lewis did is we combined the high-res 3D dust maps, in particular the Fraunhofer version. We took O-star parallaxes of all the O stars in this volume, and then Lewis went ahead and did the 3D Monte Carlo radiative transfer, and calculated the transfer of Lyman continuum photons from each of these O stars based on their luminosity through the 3D structure of the ISM. So this is actually one of the things I think these 3D models are built for is basically radiation transfer, and Hannah has been pioneering this. I mean, we had a little easier in a sense than what Hannah presented because we do all of this with only 87 stars. Okay, so it turns out that there's other difficulties, but the number of stars is not a problem. Although even characterizing 87 stars was a pain. The number of stars you had to deal with, oh my God, we would have never done this project. And here is the face-on H alpha map that you get. I just want to say a couple things about the results we have so far. First of all, we feel like we have a relatively good match between the intensity and morphology of the H alpha sky. We put in the known O star locations and luminosities, the dust maps, and we got out the H alpha sky. That's pretty impressive for a first try, I think. And it started in October, by the way. This paper, the very first plot for this paper was in October. We find that of a total Lyman continuum luminosity of the O stars of 10 to the 50 photons, we can track all the photons and find out what happened to them. And we find that 15% of the photons went into dust, 64% went into ionizing higher density gas, which would be a classical H2 region. 11% went and produced a low density warm ionized phase, and 10% escaped the simulation volume. For those of you who know about the warm ionized medium of the Milky Way, these are actually numbers that people have been saying for decades. So our simulations are simply confirming what the observational estimates have been saying so very long. Another thing, and this was actually turned out to be the most computationally intensive, was the scattering of the H alpha photons by dust in the model. It takes a ton of time to do that. These simulations, the rate of transfer simulations, run in a matter of an hour or so, and then it takes a couple days to do this last part. So that's a tough part. But it turns out of the high latitude H alpha emission, based on these models, where we know where the H alpha photons are emitted and we know where the dust is, so we can see what fraction gets scattered back into our line of sight. About 18% of the latitude above emission above 30 is actually scattered into our line of sight. The final point that's sort of, I think, important is this is a face-on view of the Milky Way and something we can observe, H alpha. At a resolution that is good as you can get. The only way you can get better than this resolution is to look, the only galaxies you can get this resolution on are in the local group, if you have a resolution of 0.1 so 1 parsec resolution in the physical models is 0.12 arc seconds at 2 megaparsecs. So suddenly, this little patch of the Milky Way is the highest resolution H alpha image of a galaxy that we have, if you believe the model, okay? So should you believe the model? Well, one other thing I just want to show you, geometry makes a big difference. I call this a tale of 2 O stars. These are 2 O stars of nearly identical luminosity. One that is the principal source of ionization in the North American Nebula. One which is the principal source of ionization for the Gum Nebula. What a big difference, right? It really matters. Basically, the Gum Nebula is poked full of holes, and technically we live inside the Gum Nebula Strömgren sphere. So the Gum Nebula ends behind us, and it's sort of a weird thing to think. And so the ratio of volume affected is 827 with the same O stars, but just different geometries. Another thing you could do is you can just now we're just playing, but we can actually look at these various H2 regions in 3D. This is the whole structure is the Orion-Arrhenius superbubble. And you'll notice there's a bright thing here. By the way, this is the model now. We've already switched to the model. You'll notice a bright structure here that replicates the Lambda Ori H2 region. And you think, oh, look at that little classical spherical H2 region, until you rotate it in 3D. And so now we can see the Orion-Arrhenius superbubble from different directions. And you can see that that Lambda Ori is actually a dimple on the back wall of the Orion-Arrhenius superbubble. which gives you a very different sense of what you should be expecting from that kind of H2 region, because you're just seeing it project and it looks like a sphere. By the way, speaking as a person who's worked on the Wisconsin H-alpha mapper, which is a velocity result H-alpha survey, knowing the 3D geometry means you can really start to make sense of all the velocity features. So I'm really looking forward to that. I retired at the right time. I retired recently, and now I'm going to devote my life to this. So I sort of think of myself as I'm a very postdoc, okay? So some other tests of the simulations, we can look at H2 region by H2 region comparison. We can predict absorption line columns because we now know the ionization fractions of multiple ions in every position in space out to a kiloparsec. We can do multi-wavelength predictions of optical emission lines. I'm also actively working on pulsar dispersion measures. We will need to add the other sources of ionization and ideally extend the dust maps further. And then future extensions, so you may be able to use this then. Once you know, this is like a chain reaction in the local ISM. You get the dust maps, you get the gas maps, assuming constant gas to dust. Then you can ionize it, and you get the ionization fractions, and then you know the ionized gas, and then you can get the magnetic field structure where you have the rotation measures that depend on both the ionized gas and the magnetic field, and so on and so forth. So it all starts at the dust maps, and hope to God they converge. But essentially, there's a wonderful chain of reasoning that we can follow as a community. So finally, the last few things I want to show you is I just quickly working. One of the things you discover when you look, this is slicing the local volume vertically. So this is the galactic pole, sort of like what Theo was showing, galactic pole, south galactic pole. This is just showing which longitude is sliced. So we're slicing around the solar neighborhood like an orange. The contours are showing you the total hydrogen density, and the red scale is showing you where the gas is ionized. And so you can see the gas is ionized in these very sharp layers. Basically, it's cloud surface ionization. One little side note, if you didn't know where H1 and H2 came from, it came from the Spitzer's papers. And he actually says, I fear that I'm responsible for that notation. And so H2 region layers are what dominate us. And our pulsar dispersion measures are not as impressive as our H-alpha. We get a correlation between observed and predicted, but a scatter of about a factor of 3. But you can sort of see why. I mean, you have to get these, when you look at a given sight line, you really have to get the details of all these interfaces right. This black line shows the total hydrogen column density as a function of distance in this direction, and then the red is what's being ionized. So it's very, very sensitive to getting all the details of the ionization right. Finally, a couple things. I'm going to take you, I don't have a lot of time to describe it, but we're going to take you through the ISM flying through, starting here at the sun, passing through the Orion-Nerinda superbubble, turning left, passing through the GUM, then returning and passing over towards the North American Nebula, and then coming back home. But the field of view on the left will just be this cone on the right. And I'll take you on the journey and describe it more here in a second. But all the H2 regions here are labeled. So you're sort of getting a fly across the galaxy sense, and you can see the excitation because this is actually in multiple emission lines. When everything's look blue, bluish, you're getting the high excitation emission traced by O3 emission. So we're almost home, and there we go. Okay, so a couple more things. I will have to truncate my talk a little bit, but we are now, with Lewis, working on trying to put in some understanding of the time-dependent effects of this thing on our maps of the 3D solar neighborhood. Because, of course, this is a static photo in a simulation, but we know there are explosions. We know there's energy input. How do we put that in with hydro simulations? So we're going to zoom into this region of the dust maps. That's this picture. And these are two hydrodynamical simulations. This one has been post-processed, only assuming photonization. So we turned off all the knowledge of collisional ionization and temperature and just reionized it to make it sort of comparable to how we were doing the solar neighborhood. And this is the full hydro simulation, where you can see young supernova remnants showing up in emission lines that you will not get if you just do a photoionization model. And so I'm going to end here. This is actually just a short movie of basically of a kiloparsec box of a hydro simulation, but it's to help give us insight on what we might be missing in the H-alpha and multi-wavelength emission sky. In these movies, the X's are the locations of O stars. The bigger the X, the higher the Lyman continuum. These are all just coming out of a simulated version described in previous papers by Lewis. The red dots are B stars, so they don't emit a lot of ionizing photons, but they do explode. And then when an explosion happens, you'll see a ring propagating outward at 50 kilometers a second that fades in 2 megayears. If you don't know, this is a lot. This will go by a little fast. So watch right here. You will see a star be born, emit a jet of radiation, fill out an H2 region here, and then explode. So let's just watch that. Boom, there it went. So we can look at this, and sort of by eye, we can try to match the morphology of the ISM to what we see, and we get a star formation, a supernova rate that's similar to Swygen. So again, consistent ideas of how the energy is being pumped in the ISM. So I'm going to end with a little sky movie of what that same simulation looks like in a color table that's colorblind friendly. Sorry about the previous ones. And I'll end with a summary here. We know a much better understanding of where and when stars formed and the sources of supernovae. We see evidence of the energy input, and now we can produce photonization models of the whole area. So thank you.
Questions for Bob? Oh, this is really cool. That's like really cool work. For the first project where you have the 3 different clusters, where's the sun's natal cluster? In that animation you had going backwards, it seemed like the sun didn't really fit in any of those. So is the sun born in a cluster or no?
Well, this is only tracing back 70 megayears, right? So the sun is actually moving in and out of this whole region because it's actually got some large epicyclic motion. So we'd have to go back many gigayears, right, to follow the sun's cluster. And of course, presumably, we've lost track of all of our siblings that used to be part of the clusters. So really, we can only go. Recently, cameras submitted a paper that tries to trace cluster evolution back a few additional tens of gigayears, and argues that maybe we're seeing velocities, megayears, yeah. Sorry, no, yeah. And so we might be seeing evidence of the kinematics of of what affected the molecular clouds before the stars formation we see. Sorry, I stumbled on that, but get the idea.
Thank you so much. I'm particularly interested in how you guys derived this supernova rate. It looks like you used a best fit IMF, and how dependent is the supernova rate on that IMF?
I knew someone would ask that, and I've been researching that in the last day. So I don't feel like I can give you an answer right now, but catch me by Friday, and hopefully I'll have a better understanding. One of the reasons I say this is because I know that the IMF in the Swygen paper and the IMF and the McCallum paper are different. And so we have to be a little careful about the comparison.
All right, one last question. Who's really, really excited about their question in particular?
The local bubble is, the H2 region is stimulated by a B star, not an O star,
right?
Still in CMA. So you've left the B stars out of this calculation. So you might comment.
They're going in this summer, especially the one problem we have with putting in epsilon Canis majoris is the dust maps that we're using have a big hole cut out in the inner 69 kiloparsecs, and so the dense 69 parsecs, yes, yeah, these factors of 10, or 100,000, but anyway, but yeah, so we need to find some way of properly filling in.
Talk about H-alpha and photoionizing Lyman continuum, but what couples the two together is Lyman alpha. Mm-hmm. And there's now new data coming out of the New Horizons spacecraft. So you ought to try to see if that fits in with your model.
Yeah, in principle, with the models we have, we could start to look at the Lyman alpha transport, although that's a very, very tricky question.
Top one, yes.
Yeah, so, but it's certainly worth a shot once we have the local bubble filled in a little bit better in the dust maps.
Okay, let's thank Bob again.
Thank you.
And next up,
we have Claire Murray, who will be talking about a galactic eclipse. The SMC is forming stars in two superimposed structures.
Thank you, Catherine. And hello, everyone. I'm really excited for the opportunity to tell you about this project. It's one I've been working on for a long time, and I hope that by the end of my talk, you are as convinced as I am that the SMC, or the Small Magellanic Cloud, is a really exciting and interesting system. But of course, because we've spent the morning talking about our local interstellar medium, and this is our first step outside, I thought I'd give you my boilerplate proposal statement about why the Magellanic Clouds are interesting. We have, of course, the large Magellanic Cloud over here and the small Magellanic Cloud down here, named so because one looks large and one looks small. And they're great laboratories for ISM astrophysics for two reasons. One is they have diverse interstellar conditions, and by that I mean they are not the Milky Way. We have more data points, more, in pretty much any parameter space you can think of, we can get more of a lever on how the physics of galaxies operates. But of course, also, it's because they're extremely nearby. These two systems are about 50 to 60 kiloparsecs away from the sun, which means that we can resolve individual stellar structures and also interstellar structures. So, they're one of the best places for actually looking at the detailed interplay between the stars and the ISM, which is, of course, what has brought us all here this week. Oh yeah, more beautiful pictures. This is all from press release images, mostly from JWST. Thanks, Office of Public Outreach. In this talk, I'm going to focus in on the SMC, which is not the most commonly focused on of the Magellanic Clouds. The Large Magellanic Cloud is bigger. It's easier to understand, and I will tell you why. The SMC has a particularly special environment, and this is just a lovely picture of it from Herschel Heritage, showing that it is, full of dust and has a lot of star formation activity going on. But when you look at it as sort of like a baryonic ecosystem, we start running into some interesting puzzles. And the first that caught my eye was that the SMC is, quote, strikingly bad at converting its massive reservoir of atomic gas into dense, cold star-forming clouds. So these are maps of, on the left, atomic gas column density from H1, and then on the right, molecular gas column density inferred from CO emission observations. And so if we want to start thinking about this galaxy as a system and start to understand how we're converting these, the diffuse gas into dense gas and then into new generations of stars, we need to start making assumptions about its geometry so that we can convert our column densities into estimates of mass and density. But the problem is that there are many open questions about the line of sight structure of the SMC. And so to start to explain what I mean by that, we're going to start with the structure of the SMC as painted by stars. And so this is a view of the LMC-SMC system. The LMC is closer to us along the line of sight. The SMC is a little farther away. And when we think about old stars, we see that they're about sort of spherically distributed around a center of mass. When we look at stars for which we can measure accurate distances, however, the picture starts getting more complex. If you look at Cepheid or R. Lyrae, you can see that the SMC appears to be elongated by about a factor of 4 along the line of sight. So really, when we're looking at the SMC system, we're looking at a Sgr A end-on when we're looking at the Cepheids and R. Lyrae. There's been a lot of work to characterize the structure on each side of the SMC. We see that the eastern side of the SMC is deeper than the western side. And then when you look also in the east, you see that red clump stars show a bimodality in distance. And so once you start piling up all of these pieces of evidence for what the structure of the SMC is, it's not entirely clear what all these pieces mean together and what that means for the history and evolution of the galaxy itself. When we look at the gas, which is where I come from, my background is in neutral hydrogen 21 centimeter spectroscopy, we also see that the SMC looks like a train wreck. And so, of course, in 21 centimeter observations, we have access to the radial velocity axis. And so when you take your gorgeous observations of the SMC from the ASCAP telescope in Australia, and you tip your 3D cube on its side to look at the radial velocity structure, you see something that looks like this. And I can't explain to you what this is. Like there's arms, there's pileups, there's voids, and it doesn't look like a very coherent system. And this, of course, is not surprising because we know that the LMC and SMC have had a dramatic history together. We're still arguing about whether they're on their first infall or their second infall into the Milky Way halo. Their interactions together have produced an enormous gaseous system known as the Magellanic System that we heard about from Sapna in her flash talk earlier. And so it's just clear from every observation we've done of these two structures together that clearly they've interacted with each other and had influence, had a strong influence on their present day structure. However, to make the picture even more confusing, when we look at the radial velocity field integrated along the line of sight, the SMC looks like a perfect rotating disk. So this is the radial velocity field of the SMC from H1 observations. And if you were to look at this, you would say, oh, great, it's a rotating disk, done, fit a rotation curve, derive a mass. And this actually, this rotation curve has underpinned our understanding of the SMC's mass for decades. Yeah, it's our best constraint for the total mass of the SMC. But it doesn't necessarily fit in with all the other pieces of evidence for what it is. And so we took a look at this 5 years ago now, with the advent of Gaia and our ability to measure proper motions of stars in the SMC system. We compared what the rotation model would predict for young massive stars in the SMC with what we actually observed the proper motions of the young massive stars in the SMC would look like. And so, of course, there's a big difference between the model and the observations here. We can see that these young massive stars, which we are inferring to be tracing the motions of their parent gas clouds because they're spectroscopically confirmed O and B type stars that we make the assumption are still moving along with their parent cloud nurseries. We see that there's a ton of variation here. There's evidence for tidal interactions from the LMC and then a bunch of other stuff that doesn't look like rotation. So, what is the conclusion here? I've spent a lot of time trying to convince you that this is a complicated system. How can we make progress? So what we did to look into this further is to dig deeper into the radial velocity structure as seen from the H1. And so what we noticed, which has been noticed since the 1950s when these observations were first started, is that across the face of the SMC, H1 is organized into multiple peaks in radial velocity. So this plot just shows, as you step across these different positions of the galaxy, you see that there are multiple structures, one at low velocity generally and one at high velocity generally. So we have a low velocity component and a high velocity component. And so to get into how this whole project fits into the interstellar theme, what we did is we identified a sample of red supergiant stars from Apogee and Gaia, which we did the same trick of making the assumption that stars that are young enough should, on average, be moving with in the same sort of 3D motions as their parent gas clouds in order to sort of fill in the gaps of information of adding a velocity component to our gas clouds that we get from stars. So we identified this sample, and then we looked at the difference in extinction observed for these stars in the two different velocity components. So here's an example of a region, of the SMC. We identify stars at low velocities and high velocities, and then compare what the average extinction to the stars at low velocities is to the average extinction at high velocity. And where we see a difference, we can then infer which of the velocity components is in front along the line of sight. This is just a relative measurement. If there's more dust towards the low velocity component than the high velocity component, then we assume that the low velocity component is behind. Conversely, if we have more dust towards the high velocity component than the low velocity component, then the high velocity component is behind. And so we can do this across the face of the galaxy over many trials which try to take into account the influence of outliers and our sort of assumption about the connection between the stars and their gas clouds. We end up with a map that looks like this. Basically, the orange and purple colors are telling you that the difference in extinction between stars at low velocity versus high velocity changes as you move across the SMC in ways that have sort of startling spatial coherence. So we see that over here we have gas at low velocity is in front, where you see orange, and in purple, gas at low velocity is behind. So what we infer is that the order of these gas components actually changes as you move across the face of the SMC, and it does so in ways that don't appear to be random. And so from this, we were able to separate our stellar sample into stars that are in front and stars that are behind. And we find that they're, both samples are, distributed across the face of the galaxy. We find them pretty much everywhere in both systems. We can then compare, start looking into what kinds of other differences we might find between these two samples. And here I'm showing a radial velocity versus right ascension map of carbon monoxide emission in the SMC as one example. And we see that if we compare the CO data with what we infer for the front and behind samples, we find that the front component is responsible for most of the CO emissions. Basically, we find most of the CO emission in our front structure as opposed to the behind structure, which, although it crosses over, we can't rule out that there isn't any CO there. It doesn't appear to be where most of our star-forming dense molecular gas is, as traced by CO. From the apogee sample, we also have access to stellar metallicities, and so we can look at the metallicity difference between these two samples. And we see that the stars in the front component seem to have, tend to have higher metallicities. We find the highest metallicity sources in the front component. And so this is all pointing to maybe a new model in which these two structures are not only, at different positions along the line of sight, but might have different physical properties. Because we have access to the 3 velocity components for these samples from Gaia, we can also look at their kinematics. And so here I'm showing the radial west and north velocities for the front sample in purple and the green and the behind sample in green. We see some interesting structure that has already been known. This sort of slope that we see in proper motion to the west is heavily indicative of tidal disruption by the LMC, which has been known for some time. And if we extend our model, we can then actually separate the two gas components, or separate the gas into the front and behind components, and infer that they actually seem to have similar mass. So we find the similar column density in both the front and behind components. And these are the two maps here showing everyone's favorite features. Here we have the SMC bar, and then here's the wing feature, but we see gas in both components across the system. So really the sort of interesting result here is that not only are we looking at a system that is highly disrupted along the line of sight, but the two systems are sitting right on top of each other, which is what makes them hard to distinguish up until this point. And so I mentioned the model that we ran in order to estimate the properties of these structures, but didn't talk about it in too much detail. I'll show you what the results look like. So our new picture for the SMC is that it's not one single system, but two structures. They're separated by about 5 kiloparsecs along the line of sight based on a very simple toy model that we wrote about in this paper. The front one seems to be rotating a little bit, but that's highly uncertain. But we're excited because the new model is consistent with our previous understanding of where the gas was along the line of sight from other methods. Work by Petya Yanchulova, America Jones showed that dust in the southwest bar is pinned to about 62 kiloparsecs, which is perfectly consistent with our model. And our new picture is not inconsistent with the one that is painted by stars, which shows that there's a lot of substructure, in particular, 2 components in certain places. All right, so I think, okay, so the SMC has 2 things, who cares? I think the reason why you should care is because, and sort of as part of the theme of this conference, I think our view of the interstellar medium, both locally and in extragalactic systems, is coming into extremely sharp focus right now and in the next 5 years. This was our H1 view of the LMC and SMC and the bridge connecting them. With the advent of the gas cap survey, which I mentioned, we're getting down to 45 arcsecond resolution for H1 in these systems, which will allow us to even further refine our knowledge of where they are, where they're coming from, and where they're going. And so with that, I will leave you with my conclusion that the SMC is not simple. Synthesizing ISM and stellar tracers is key to unraveling these mysteries, which will let us not only think about this galaxy as its own special snowflake, but think about the mass budget of the ISM at low metallicity, dwarf galaxy interactions, and also the formation history of the Magellanic System. And so I'll take questions with that. I must be over time. Yeah.
Questions for Claire?
Hi, it's very interesting, but I am kind of wondering that if you look at the structure with the Cepheids and our Lyrae, you don't see two different structures. You see an structure with the Cepheids. So I'm just wondering how that reconciles with what you're seeing, which you're saying are two different structures that are separated.
Thank you for that question. So I think that the picture isn't totally clear. I think there's a need, and part of my soapbox picture is to get the numerical simulations to include the SMC in their calculations. Very rarely do they ever consider it because it's so there are so few constraints for its geometry. But I think the substructure there, you do see some substructure in the Cepheids, and thinking about the timescales is key, because it's possible that the particular interaction that may have disrupted the SMC might have resulted in like a large stellar halo of debris structures around the two gaseous systems. And so we won't really be able to say more than that. We basically can't say that it's inconsistent or consistent until we have a better handle on the dynamics from the simulations.
You go ahead.
Thanks for the talk. So people like Johnny Henshaw and Eric Koch who have done all of this work, kind of decomposing spectral cubes along the line of sight into many multiple components rather than just like front and back, I guess. So have you tried that, and what kind of things do you see?
You mean like Gaussian versus, like lots of different components besides just one or two? Yeah, I mean, I have. So part of this work involved a decomposition of the data into multiple components. The signal to noise that we get for such a measurement of measuring extinction towards these sources is really low, and so doing more than front and behind gets really difficult, except in the areas in which you have more dust. I mean, the SMC is actually really diffuse outside of its like massive star forming regions. And so I was hesitant to do anything more complicated, but this, of course, is just a first step. It's basically, as I said, my ploy to get people to look into this more and tell me I'm wrong.
Okay, so one last question while Christina gets set up.
Thanks, really cool. I was wondering, how do you think we should think about this system? Is this two dwarf galaxies that are, or is this a tidal debris that you're seeing pulled out? What's going on here, in your opinion?
I mean, this, was the first paper that I wrote that like a journalist wrote about and was like, oh my gosh, it's two galaxies. Like there's two dwarf galaxies. It's not one galaxy. We definitely didn't say that in the paper. And so it's not, we don't know the answer to that, but I think there are several possibilities. One is that, it is the two structures are remnants of two galaxies, because we do see differences in their chemistry. But what is also likely is that, the behind component could be tidal debris structure, the so-called counterbridge of material going behind the main SMC remnant. I will say this idea of multiple structures has been around since the 1970s with work by Matthewson and Ford. And so we're not saying something totally new, we're just refining the model and showing exactly where these substructures might be sitting. And so it's not like totally out of left field, but yeah, the answer is we're not sure yet, but hopefully we'll find out.
Okay, let's thank Claire again.
Oh boy, where did I put it? Oh.
Okay, set it.
What's starting in the center for some reason? Sorry. Wrong way. There we go.
Okay, next up we have Christina Lindberg, who will be talking about mapping the ISM at parsec scales with dust extinction in nearby galaxies.
Hello, can people hear me? Wonderful. I see nods. Yeah, sorry for the long title. I tend to put everything I mean into the title. Hi, I'm Christina. I'm a final year grad student at Johns Hopkins across the street. So I want to thank the organizers for the incredible timing of this conference, as I'm about to defend in a couple months. And I'd also like to, thank the organizers and the ISM STAR group in general for having been a huge home for research for the past 6 years now of my academic life. So I'm incredibly excited to present on some of the work I did for my thesis today. So to start off, I don't think I need to do much motivation to tell people that 3D dust maps, especially in the Milky Way, have been trailblazing a whole new level of insight into small-scale processes such as fueling star formation, or what's fueling star formation, what are stellar feedback doing, galaxy evolution as a whole. And I think a lot of times when I give this version of this talk, it's to broader galaxy people, and so I've had to flip my motivation, right? We're going from small scales up now rather than going from galaxy scales down. And so I think as was pointed out by Claire briefly, I think one of the only major limitations for staying inside the Milky Way is that we have limited insight into how metallicity variations can influence a lot of the ISM physics that we know of. So for example, in the early universe, we know that there are fewer metals being produced, and that ends up having a huge influence on not only star formation, but also the types of feedback processes that stars are producing and galaxy evolution as a whole. So if we want to understand this from first principles, from the early universe, all the way up until the present day, we need to get a better grasp on what the ISM is looking like at these lower metallicities. And so my proposed solution for studying this is to turn to nearby galaxies. So like was briefly introduced previously, there's local group galaxies can give us a lot of very powerful insight into these early chemical processes. And so here is just some of the local group MVPs. This is definitely not all of them, and the definition of the local group depends on who you ask. And so I cut it off at a megaparsec because otherwise the slide got too complex. But I have just a couple of them, and as you can see, as pointed out earlier, we can look at the Small Magellanic Cloud, which is at a distance of 60 kiloparsecs. It's at roughly a fifth solar metallicity. The Large Magellanic Cloud is even closer. It's at half. But as you can see, there's a lot of metallicity variations within the local group at different distances. And what's really key when we're thinking about ISM and galaxies beyond the Milky Way is what sort of inference we can garner. And so for, if we look in on a region within the Large Magellanic Cloud with something like Hubble or James Webb, we can get really high precision photometry and actually resolve individual stars. Now this is at 50 kiloparsecs. Again, we're 8 kiloparsecs away from the center of the galaxy, so that's not a huge leap. But I want to motivate the fact that even more than 10 times further out in something like M31 at nearly a megaparsec, we're still able to resolve individual stars with something like HST or JWST. And I think off the top of my head, 3 megaparsecs is roughly where we start to struggle in terms of resolving stars, but we can go into outskirts of galaxies and do lots of cool stuff there. But what's critical about this is that if we can characterize individual stars by resolving them, we can actually infer the amount of extinction through their spectral energy distribution, and thereby use dust extinction as a phase agnostic tracer of the ISM, similar to how we're doing stuff in the Milky Way. And so to just briefly motivate, this is kind of similar to the Brutus methodology that was introduced this morning. So the intrinsic sort of assumption that we're making here is that every star has some sort of stellar spectrum, and that's informed by its luminosity and temperature and gravitational evolutionary state. However, if there's any amount of dust extinction along the line of sight, this dust will extinguish the light from the star, from the spectrum, and we end up, what we're actually observing is an extinguished stellar spectrum. Now, distance will limit or will lessen the luminosity of a star equally across all wavelengths. However, dust is unique in that it will generally preferentially extinguish shorter wavelengths, which is very critical because that means that if we observe, from the UV to the infrared, we should see differences in the extinction onto the observed spectra, and thereby that means we can break the degeneracy between stuff like distance and dust, and actually end up inferring the amount of dust along the line of sight. And so What's even cooler, though, is that we don't actually need spectra to do this sort of inference if we just happen to get enough photometric measurements in order to get a rough shape of the spectral energy distribution. We can do a very similar inference. And if we do that, that means we're able to do this with photometry rather than spectra. That means we can get extinction measurements for thousands of stars at once rather than just a couple hundreds. And so to do this, I use something called the Bayesian extinction and stellar tool. This was developed by Carl Gordon here at the Institute. We'll be having a session on this on Friday during the Hack Day sessions, or the Hack Day afternoon. And so if you're interested in figuring out if you have a data set that could be modeled and analyzed in a similar sense, please stop by and ask us some questions. And so for my PhD, I worked on a survey called the Sgr A survey. This is a pure parallel 500 orbit HST imaging survey. It was operated alongside the Ulysses survey. And essentially what that means is that every time Ulysses took spectra of a massive star somewhere in the Magellanic Clouds, we got to open wide field camera 3, or not every time, but oftentimes we got to open wide field camera 3 and a slight off angle, get some extra data. And that was, try and see get as much filter coverage as we could. And so this was very valuable because that meant we got UV to infrared photometry with wide field camera 3 for almost 90 fields with varying filter coverage, so anywhere from 3 to 7 filters. And so you can see we got a lot of interesting coverage in the small Magellanic Cloud, and we got a ton of coverage in the large Magellanic Cloud as well. I should note that these denoted figures are from a similar survey called the Metal Survey, which Julia Roman Duval was also involved with. So if you're interested, Claire is the PI of the project. We have a paper on this, which you should check out if you want the nitty-gritty details. But so what I was very interested in is saying, okay, so we have gorgeous, for example, color images of this data. But if we actually extract the point spread function, get the resolved stellar sources in each of these fields, and run our Bayesian analysis and then extract the extinction, we see that there's a lot of interesting structure going on in these images. So we observe stars with anywhere from 0 AV up to 3+ magnitudes of extinction, and there seems to be some amount of structure, but it's kind of confusing to infer. And so one of the things we have to consider when we're doing this sort of analysis is that we're looking in an external galaxy. And so there's going to be stars both in front and behind the gas in this galaxy. I should note this field in particular is from the Large Magellanic Cloud, sort of near the 30 Doradus region. So it's pretty dusty. But we're seeing both stars in front of and behind. And so if we end up doing a selection process by which we manage to isolate just the stars behind, we get a much more clear sense of the picture. And so between this slide and the next slide, I'm just going to shift the stars slightly so that they're more oriented on an XY grid. I'm going to trim the color bar so that we can hopefully get a better dynamic range. And so this is what the point sources look like. They're ranging anywhere from 0.5 magnitudes to 4.5 magnitudes of extinction. And it's interesting because it's 5 parsec scales that we're, sub-parsec scales that we're probing here. And so, but these are only point sources. Traditionally we might bin them and take some averages or something like that, but really we can leverage more cooler resources like Gaussian processes and interpolate between these sources to get an image of the underlying structure of extinction in this field. And so I'll stop here for a second and just point out, we're seeing very interesting blobs here on the left, and there's sort of a lack of material here on the right. But I should note, this is still 1.5 magnitudes of extinction, so this is still fairly dusty, and there seems to be little blobs. And so, off of first principles, this looks pretty decent, but what's really cool is we can compare this with ancillary data or ancillary tracers of the ISM. So for comparison, we happen to have dust infrared emission by Chris Clark. So if there's questions about this data, I'll just relay them to you. No, just kidding. But what's really cool is we can compare the dust infrared emission. This is a 100 micron Herschel. We can directly compare these, and we see that there's very similar morphological shapes and structures going on here. There's a clump down here. That looks great. And there's this sort of arc coming up here. And so this is a wonderful confirmation that hopefully, even though this dust extinction map was derived only with point sources that we were fitting, we're actually recovering physical structures even at a distance of 50 kiloparsecs. We can go further and we can compare with something like molecular gas. This field happens to have super high resolution ALMA data from Tony Wang's 2022 paper. Most fields in the SMC and LMC do not have this level of ALMA coverage. So this is a very unique opportunity to compare. But we can see here that there's this similar molecular gas structure on the side here that we definitely captured with our extinction maps. However, there's a lot of interesting little clumpy structure up here that we occasionally maybe we're capturing some of, but not quite sure what's happening there. So that's an ongoing point of exploration. We'll definitely be writing a paper up on that in the future. But this could be, is very useful then because we have an underlying tracer of both the molecular gas and how that flows into the atomic gas. And so we can get a constraint on the fraction of molecular gas that might not actually be traced by CO in this sort of environment. And so there's going to be a ton. I should also lastly point out that what's really cool about a lot of this sort of dust mapping is that it's dependent on the source density. So how many stars do you actually have to probe? And so this means that we're not constrained or nearly as limited by distance. And so as long as we can, the source density in the Large and Small Magellanic Cloud isn't that high. And so as long as we're able to resolve individual sources out to hundreds of kiloparsecs, we should still, the resolution shouldn't, the spatial resolution of these dust maps shouldn't be 1 over distance squared like we usually see as issues with emission-based tracers. And so there's going to be a ton of cool science enabled with these extinction maps because they're providing a fully independent benchmark tracer of the multi-phase ISM. So we can, like I already mentioned previously, we can look at how dust emissivity changes as a function of metallicity. We can also compare, the spatial distribution of dust and atomic gas and molecular gas, calibrate these relations, and constrain the fraction of the CO dark molecular gas in some of these regions. And last, one of the things I'm really interested in is comparing the ISM morphology, trying to characterize this at lower metallicity at parsec scales, and seeing how that ultimately ends up impacting star formation and feedback at these parsec scales that are typically not really probable in external galaxies. I also want to motivate the fact that we have a lot of panchromatic coverage of galaxies in the local group now. So there was a recent survey that came out. Carrie Goldberg is maybe somewhere in the room, but there was a paper from a survey called the Levitt Trajectory, led by Carrie and others. And they got panchromatic coverage, not of M30, all of these galaxies, but they expanded our sample of galaxies with UV and IR coverage a while. So there's a lot to analyze, and I'll leave it off here. Thank you.
Thank you, Christina. Questions?
Now that you've started to get dust structure, have you done any further characterization of, say, bubble size or anything like that compared to the Milky Way?
Bubble size, you said?
I said bubble size, but any characterizations beyond just the H1CO correlation?
Yeah, that would be really cool to do. I think at the moment, the biggest constraint is the fact that we're only getting individual HST fields. And so we can get snapshot measurements across the small and large Magellanic Clouds, but we're not getting really a continuous or contiguous coverage. And so characterizing, what is a bubble versus what is half of some other feature is. What
you're saying is wait for Roman.
We should definitely, yeah. That was the other thing I forgot to motivate. Yeah, Roman would, full coverage would be unprecedented in the opportunity for this sort of work. There is full contiguous coverage though of M31 and M33 though, so that could be a very cool opportunity and something I'm looking forward to exploring in my postdoc. Maybe the way to put it.
Online, yeah.
Online.
Yeah, I'll read it out. Question online from Mode. What kind of quality cuts were applied to the beast fits to create the dust map?
Yeah.
When high AV is recovered, what type of chi-square would you use?
Yes, so we implement a lot of quality cuts in our beast fits. We originally fit probably over 1 million sources in the Magellanic Clouds, and I think only a third ended up in our high reliability catalog that we deemed, decent fits. I will, rather than trying to verbatim remember all the cuts we put in, I will reference or refer them to Lindbergh et al. 2025, because there's a huge section on that there.
Other questions? Someone who hasn't asked a question yet? You asked a question? Oh, wait, you already asked a question last time. Anyone else? Have you asked a question recently?
Yes. Well, I've already asked a question.
Okay, it's fine. Go ahead.
Very interesting results. You already showcased how the map compares with one of the infrared bands.
Mm-hmm.
You also compared with other infrared bands.
Yeah, I can make those maps. I just didn't put them all in the slides, but yeah, we can check.
How do they compare? If you not checked it?
I haven't checked it yet, but I have the process pipeline to make the maps already if you want.
Other questions? Okay, yeah, go ahead.
So one of the fun things you get out of fitting a Gaussian process is that you get a scale length, right, that tells you something about how the wiggles, like the spatial scale over which the wiggles vary.
Mm-hmm.
So have you looked much into that and kind of compared it to, like, is it interesting, I guess is the question.
Yeah, so I did generally find that you need at least 2 scale lengths to properly characterize the ISM on, here we go. There's a good, you needed at least 2 radial basis functions in order to characterize the structure. And that is, in my upcoming paper, I definitely want to explore, especially for broader kernel, the broader kernel scale lengths, how does that compare, for example, to the H1 structure in the field? I mean, this field might be a bad example because there's a lot of molecular gas, and that's definitely the dominant source of emission. But, is there the length, when we see 2 best fits with 2 length scales, is that being driven by different gas phases that we're tracing and stuff? So, yeah.
Okay, let's thank Christina again. Some so advanced endpoints.
Mm-hmm.
Good.
Mm-hmm.
Okay, and next up we have Alexander Plavin, who will be talking about using quasars as lighthouses for the ISM fog.
Yeah, hi everyone. I'm currently a postdoctoral fellow at the Black Hole Initiative at Harvard, and generally I mostly study active galactic nuclei, quasars, and the ISM, it's been moving for me from the annoyance you need to take into account sometimes when studying AGNs to an object that we can and we do study. Today I'm very excited to mention some recent results on the using quasars as lighthouses to shine through the ISM, and I hope to convince you that first, these kind of studies, it brings unique handles on the ISM, especially on the turbulence, and that we are really now in the prime time and will be in the near future to use this method of study. So the idea generally is that radio waves are affected by anything with free electrons. And this, in our galaxy, it mostly means interstellar plasma. So there is some distant quasar, AGN, and the radio emission from the jet comes through some clouds of gas and like ionized gas and plasma, and then they get scattered or refracted before they get to the Earth. And this effect is, this phenomenon, it brings two observable effects. One is the angular broadening, and another is so-called substructure. So here I try to visualize both of them. This is a simulation. The intrinsic source size, if there was no scattering, would be like a point source here at these scales. But here there are images at 3 radio frequencies, and you see that first that they are really bigger than a point. This means that there is angular broadening that is very, very frequency dependent. All of these are at the same scale. And also you see that there is some substructure, like especially visible here, but also in these images. And both of these effects, they are not intrinsic to the quasar emissions. They are really caused by the scattering within the ISM. So first is and most noticeable is angular broadening. It is it can cause at some regions in the Milky Way extremely strong scattering, like up to tens or hundreds of milliseconds at typical radio frequencies. And still, it is only measurable for the most compact sources. That's why quasars, AGNs are kind of prime candidates for to use for this. As for substructure, it is these kind of like ripples on top. They are similar in actually nature to what you can see through the fog or like foggy window, and they are also visible only for small sources. The source intrinsic size needs to be smaller than the typical scale of these ripples. So first, regarding the measurements and overall like studies of angular broadening, how it manifests itself. So here I just show examples of size versus frequency dependence for 4 sources. One is the Sagittarius A star, the black hole in our own galaxy, and its kind of accretion flow. It is a source with the strongest scattering. It has the largest size. It's fully scattering, really. And you see this inverse, the size is inversely proportional to the frequency squared. There are some there are sources that are less scattered but still follow this trend almost like until very high radio frequencies. There are sources that are almost not scattered. They follow the typical kind of like inverse frequency dependence that is that present and should be present for basically anything that happens within the AGN jets. And there are some intermediate cases where you see this kind of this band of the source size. And this by itself, I mean, for most of the realistic scenarios of scattering, you expect something very close to the inverse frequency squared. So here, what we measure is mostly the size of the source, the strength of the scattering. And here I just show 4 examples. But actually, we have data sets that are available for like tens of thousands of AGNs at multiple frequencies. They come from so-called VLBI. It's a very long baseline interferometry that's only possible in radio, provides the highest resolution in all of the astronomy to milliseconds and sub-milliseconds resolution, and a lot of data is public. And naturally, we can use it to first measure the apparent size of the source. That is, as everything is, can be difficult at scale, and then just map the ISM scattering over the entire sky, over the entire galactic plane. Naturally, that's what we did recently. So first, I really was measuring these AGN kind of core sizes for different purposes, for studying the intrinsic frequency dependence. But they turned out to be useful for scattering studies as well. And so here, this is just the all sky distribution, aside from the southern sky, of the VLBI sizes of AGN cores at the lowest frequency with enough data. And you clearly see the galactic plane. This is the galactic center. This is the Cygnus region, and a few other regions you may recognize. So as the observed size is effectively the sum of the intrinsic size and scattered size, this increase of the observed size definitely indicates scattering. Now, so this was kind of like, these sizes used in these studies, they were the side product of of measurements done for a different purpose. Now we are working to refine these size measurements to get rid of like outliers or badly measured sizes to make quantitative comparisons possible, not just qualitative. So the map is getting its better resolution. We get rid of some artifacts, and this is the current shape. It should be improved even further very soon. And aside from just generally noticing that, yes, there is more scattering in the galactic plane and close to the galactic center, we can compare these maps to other traces of matter in the Milky Way. So here I show the example with the H-alpha map. H-alpha is shown with colors, and AGN core sizes are shown with contours effectively. So the contours indicate regions with larger apparent sizes, with more radio scattering. And you see that generally up to the available resolution these maps trace very similar regions. So it's not just the galactic plane versus outside of the galactic plane, it's also the specific parts in the galactic plane and outside of it. So these trace similar properties, but not exactly the same, most likely. Like you see some discrepancies here, maybe the relative strength is not the same. So this is this kind of comparison between multiple observables will be probably one of the keys to fully utilizing the potential of these scattering measurements. As for more direct comparison, of course, electron content can also be probed with pulsar studies, and there are reasonably well-known and often used electron content models of our galaxy. We find that they don't fully coincide with what we measure for AGNs. So here on the horizontal axis is so each point is some bright quasar, and the horizontal axis is the size that we measure with, this is a scattering size. We try to get rid of the intrinsic contribution here, but this is effectively the measured size. On the vertical axis is what we should see in the same line of sight from this electron content model from 2001 based on pulsars. You see that there is some correlation, but it's not particularly strong, and there's definitely some effects that are that don't fully agree. So maybe AGNs can be used as another, arguably a better tracer of electron content in our galaxy, a different lines of sight, and the benefit is that they shine through the whole Milky Way, not as pulsars do. So this is for all sky studies. Another thing we can do is, after performing this analysis, is to select individual sources that are that they are located in heavy scattering regions like this one, and also that they are bright enough to be available for deeper studies with existing telescopes. So this is I'm going to show a few slides on this source. This is just a phone number, effectively, and taking these like reasonable parameters of interstellar matter and its turbulence, what we know about it, that's what we generally expect the source to look like at the lowest radio frequencies. For now, based on just archival observations, this is how it looks at different frequencies, going from higher at the top to lower at the bottom. At the highest frequencies, we don't expect and we don't see any effect of the scattering. This is just what you typically do, how you typically see AGNs. That's what these images are, what I typically study. But here at lowest frequencies, you see that it becomes bigger and bigger. The apparent size becomes bigger and bigger. The scales are different here. And it becomes aligned with the galactic plane. So this is, again, the angular broadening. We don't yet see the refractive structure. But in some of the archival observations, so I won't go into many details because this is like a radio interferometry specific plot. At the largest baselines, we have two telescopes very far from each other. You can see some hints of refractive scattering as well. But in the archival data, it is really at the limit of the noise. We can be generally sure that we see something here, but we cannot really model it reliably. So recently, just a few months ago, I submitted a VLBA proposal because with dedicated observations, we can easily get a signal-to-noise ratio up by a factor of 10, and we can get more points here to really model the source. Also, both the intrinsic and the scattering properties. Also, I plan to observe it 3 times at different epochs, basically to see this kind of variability. This is the same animation I was showing on the first slide. And this is some simulation of what the scattering screen should look like in terms of electron density along the line of sight. And this is the resulting image. These changes are expected to happen on scales of months to years. So something that is just realistic to probe. And I mean, I hope these observations happen, the proposal get accepted, and we can get the first it will be like the direct confirmation that what we are seeing corresponds to the known patterns in the ISM, and it will get us a handle on the turbulence length scales. This is probably the most direct outcome of quantifying this structure. To sum up, so interstellar matter, everything with free electrons, it scatters radio waves from distant quasars that are almost point-like, and scattering is directly measurable with radio telescopes. We can use it in two regimes. One is all sky analysis, mapping the and refining the electron content in the Milky Way, selecting line of sights that are heavily scattered for further analysis. And the second is studying prominent individual quasars. What we where I see a synergy here with other tracers of ISM is basically to constrain the distances, because these studies, they generally you can scale both the turbulence scales and the distance back and forth, and the observable image almost doesn't change. So if we know the distance to the scattering clouds that are probably the same as the like dominant gas clouds along the line of sight, we can determine the absolute length scales and the range of length scales of the turbulence, basically from the lowest to the largest, where it dissipates. So these will be probably the next years of this direction of studying the ISM. And with that, I'm happy to answer any questions and follow up. Thank you.
Yeah. Oh, Greg and then Jeff. First. Yeah.
What length scale can you measure the turbulence using this method?
So what do you mean, what length scales? So
is there a lower limit on the length scale that you can measure?
In principle, with higher and higher like SNR and the coverage of baselines, for like radiant interferometer baselines, we can cover a very wide range of length scales. It will be limited by probably how close the source is to a point. I'm pretty sure we can get all the way to like the lowest. What do you mean, the lowest or the highest?
Lowest.
Lowest. I think we can easily get to the scales where the ISM is expected, turbulence is expected to dissipate.
What is that scale actually?
I just had the number in my head just like before coming here for the talk, but
it's under a tenth of a parsec, certainly.
It's like a
few parsecs.
Yeah, much. Yeah, I mean, we can go definitely much lower than a parsec.
Yeah, interesting work. It turns out I wrote a paper in 2008 on exactly this topic, and we found the scattering distance was the order of a few parsecs, like about 5 parsecs. And also we found, and you might want to test this, look at observations at different times of the year. And you may well see an effect that when you come back to the same time of year, the pattern repeats. You're seeing an effect of the Earth's motion around the sun intercepting the pattern. And it's really interesting stuff. Keep at it.
Thank you. So within this proposal, if it gets accepted, there will be 2 observations separated by a year. I don't expect them to fully repeat each other because of the kind of turbulent changes, and we may, I mean, depending on where the screen and the Earth is relative to each other, we may not come to exactly the same configuration, but at least the properties, like the properties of the change, should trace back to the motion.
What's the impact if there are multiple screens that you're viewing through?
Yeah, so in principle, of course, all of them will can affect your source, but generally, what happens is the effect from the closest screen, closest to us, is dominant. So you can see, like, okay, the galactic center is a separate thing, but this is a Cygnus cloud. It's very close. It's basically like local, like our local neighborhood, and everything further away, it needs to be just like larger and more turbulent, more refractive to produce the same angular scale. So
I understand it with the broadening, but what about the time scale of variation? It'd be neat to see your simulation on full screen.
Yeah. So yeah, I did this. I ran this simulation for different so which is velocities at different distances. However, for this specific line of sight, it almost doesn't matter. So the velocities are really about the same in this direction, the relative velocities, be it in the Cygnus or in the next arm, Perseus, I think. Or, yeah, so the angular velocities will be about the same. Just
questions?
I was wondering how many quasars are bright enough that you could actually detect them higher than the noise to get the small scale structure, especially.
So for now, on the ground radiant interferometry array, it was only detected for Sagittarius A star, not because it's particularly bright, but because it's well studied and very highly scattered. There were, I think, 2 or 3 others detected with Spaceville BI with Radio Astron some years ago. But now with these kind of all sky studies, we can select sources more systematically, like look at those with larger sizes. And I think there is another one, we see some hints of this structure in archival data, but this archival data was not really dedicated for this purpose. It had different things. I think with dedicated observations, you can easily get like 100 if you get this time on the arrays.
Yep.
So for electron density, there's another model, YMW 2016.
Mm-hmm.
Have you thought about applying that?
Again, I will think about it. I mean, I'll look it up. So thank you for this suggestion.
Oman Karimi?
Oh, yeah, we can do that. We can, yes. Can you send it to Alex offline? Through Slack? Through the Slack channel for this workshop. Good? Okay, send it. Yes, okay, great.
Thank you.
Okay, so let's thank Alexander again. We're doing a poster flash talk up here. Where the poster goes.
I have my spread jacket too.
They're not any supporting.
Oh, we can do them.
Doesn't matter. I just wasn't sure. Not everyone looks at it.
All right, we're gonna start off with Caleb here.
I think it's probably better rather than passing it. Yeah, so just use the podium.
Yeah.
Integrated. Sure.
That is the problem.
Less trees.
Let's see.
That's it. That's a random.
Yeah.
Hi. Yeah, so my name's Caleb. This work is also on astrospheres. We heard from Seth. This time we're looking at what kind of dependence astrosphere shrinkage has with different orbital parameters. And just to remind everyone, the cases we're interested in are when we encounter either a very dense cloud or we're moving very fast, and this is a nice video showing what can happen. And so the Earth would get exposed to this cold cloud, and there could be climate effects from being exposed to dense hydrogen or also cosmic ray exposures. The main results are that if we look at action, the space of actions, So we have three different options. There's the azimuthal, which just controls the sort of guiding sense radius as the star moves around the galaxy. Then the radial action controls oscillations about this radius of the plane, and then there's oscillations. And so what we find is that for the radial action, which you can see plot, there's an overdensity towards higher radial actions because there's more oscillations in the ISM, and so you're able to probe more of the ISM. We don't really find any dependence with the azimuthal action. And then as a proxy for the vertical action, we look at the vertical velocity, and we kind of find two overdensities. One at low velocity, so stars that tend to sit in the plane, that's where most of the stuff is, they tend to descreen more. Descreen meaning when the atmosphere shrinks below some predefined radius, and towards higher z velocities because you're kind of crashing into the plane and moving quickly, and so there's more ram pressure. Yeah, if you want to hear more, my poster is over there, number 14.
Next we have Carl Gordon.
Second slide.
So you gotta do the present button.
The present button. Oh no, not play from start. Present button.
No, not full screen. Oh, because it's PDF.
That's PDF. I'm seeing this whole
Now the dust extinction goes like this. See more people up here.
Hold on, let me get in.
I think Carl should do it.
Like every extinction, it goes up.
It's Carl.
That's good enough. No, don't get that was a mistake. Ignore that one.
Carl Gordon.
All right. I have a poster on UV extinction curves and maybe some order in the chaos. If you thought the Milky Way had a lot of variation, once you start to fold in the rest of the local group, including the LMC and SMC, you find out that we have quite a large variation. And what I'm showing here is we have also adding in M31, which is ongoing work. We have a new sample of UV extinction curves. And so on the top plot, do we get to, ooh, look at that, ooh. You can actually see what we're plotting is, this is the dust column, and now this is for versus gas to dust ratio. And the interesting thing here about this gas to dust ratio, for line of sight, Lyman alpha measurement plus AV, and what you can actually see, there's a large variation. Even though in the Magellanic Clouds, you might imagine that you might get the same gas to dust ratio because the metallicity is pretty uniform in each cloud, i.e. about twice for the LMC, and in the SMC about 5 times what we see in the Milky Way. But in fact, we see quite a lot of variation, and they start to mix together. We actually see that in the UV extinction curves. And so if you look over, well, if you look here, it looks the best in this one. What we actually see is that if you look at the slope in the UV, we get very large variations in the slope. We actually see that it's correlated with gas to dust ratio in such a way that there are sight lines in the SMC that have the Milky Way gas to dust ratio and the Milky Way UV extinction curve. We also have sight lines in all the 3 galaxies that start to intermix. So it looks like there's a family of curves that it's not like there's an SMC extinction curve. There's actually, it's just the SMC is at the most extreme end. And so if you want to know more, and there's also the bump, and there's the far UV rise. If you want to know more, come to the poster. It's number 6 on the 4th panel over. All right, next we have Wilma Kiviaho.
So I'm a student from the Paris Observatory, and I will be telling you about Cepheids, pulsating giant stars, have the special period luminosity relation from which we can derive their absolute magnitude and therefore their distance. That is why they are used as calibrators in the extragalactic distance scale. However, like any other star, they are impacted by extinction. And right now, and this is especially difficult for them as they are variables to determine the extinction. Right now, there is a lot of scatter for the Cepheid threading in the literature, and this is really a limiting factor for the determination of the distance. So luckily, we have an innovative approach to tackle this problem. If you want to hear more about it, please come find me at my poster. Thank you.
All right, next we have Ben Velka.
Thank you. It turns out pretty well. Hey, everybody. My name's Ben. I'm a post-bac student at UMass Amherst working with Professor Yuan Lee. And my work focuses on using young stars that have recently formed in the Milky Way as tracer particles for their natal molecular clouds. So it's expected that these young stars retain or inherit and retain the kinematics of their native clouds for some short timescale. And this is great because you can access the 6D information, the 3D positions and 3D kinematics of these stars much more easily than you can of gas, as we have seen today. And most of the kinematics that they inherit are turbulence. These clouds are turbulent, but there's also things like gravitational collapse that can occur on different axes at different times that impart some different kinematic tracers on the stars. Also things like supernova that can create some expansion that may be anisotropic, and effects from local magnetic fields that are poorly understood. And we're trying to see how well these stars retain all of these different contributions to the natal gas dynamics in their own motions traced by Gaia. And if you want to learn about how we approach answering this question and what sorts of cool things we found out, please come check out my poster. Thank you very much.
And last but not least, we have Jim. Oh, we got one more after that?
Yes, last. Okay.
Yeah, you're last.
Last but not least. Definitely not least. Yeah, just the bullets.
Perfect. All right, take it away.
Okay. Seth Redfield and I have been working on the local interstellar medium for many years. And we're now in the process of writing a book summarizing everything that we know about within the local bubble. What I want to mention in these bullets are we've identified a number of warm interstellar clouds about on the basis of kinematics. We're now finding that these clouds are, of course, do not have constant properties. They are inhomogeneous. The local interstellar cloud, for example, a region that's co-moving, has temperatures in the range of 3,000 to 12,000 degrees. And for the first time, we've been able to identify an upper limit to the inhomogeneity distance scale, which is 5,000 kilometers, 5,000 astronomical units, or less, or much less, it could be. We're also finding locations, sight lines that have much higher hydrogen column densities than expected for that particular distance of sight line. And these are likely due to overlapping clouds, in particular the G and the local interstellar cloud, but they may be many other clouds. We do want to point out that there's an overlap between the study of the local interstellar medium and our understanding of exoplanet atmospheres. And the reason for the overlap is extreme ultraviolet radiation critically determines whether a planet has an atmosphere or not. And if it does have an atmosphere, what the chemical composition is. The extreme ultraviolet radiation we cannot measure directly because of interstellar absorption. So we have to know the neutral hydrogen column density on the line of sight to the host star of the exoplanet in order to infer whether there should be an atmosphere or not and what its chemical composition is. That, of course, is a major project with JWST. And I do want to point out that we can measure neutral hydrogen column densities to many, many exoplanets, which are located within about 50 parsecs of us. So, thank you. Come see poster number 3. It's the oversized one over there.
All right, that's all we have. Any updates from the chairs?
Be back in a half hour.
We'll be back in a half hour.
Be back here at 3:50. Thank you.